that happened again. That's a Kobalt brushless running a 4 amp hour battery, and it just sent its soul up into the clouds, as you can see. Why it always happens on the last cut? That's what we call in the industry click no crank.
I thought maybe we can give it a second chance. Oh, still turns on. Battery is on 2. It smells bad. You know, the channel subscriber counter just turned 420. I was hoping we can smoke something here tonight. Welcome back to the shrine. Happy 420. Oh crap. That's not a good idea to do it inside. Anyways, let's look inside and see why is it smoking. I picked this up on a garage sale. The guy even had the original box, as you can see. I don't know if he never returned it. It says the tool has a 5-year warranty and the battery has a 3-year warranty. Maximum speed, maximum runtime, maximum power, maximum motor life. It's a Kobalt 24 volt max brushless. Look at that, it's got instruction manual. It even has a extra saw. I don't think this has ever been taken out of the package. Look at that, original package. I think this was pretty much a crib that. Let's see if there is anything about smoking. Problem. Reciprocating saw does not work. Battery is depleted. Blade blinds. Blade cannot be removed. Saw vibrates or shakes. The LED work light blinks rapidly. The LED work light blinks slowly. Warranty. So there's nothing about smoke coming out of the unit. So let's take it apart and see what's inside. Oh, something tells me it's not gonna work. As you can see, they implemented a security, a safety feature on that screw, so it needs the safety Torx drivers. Half an hour and $7.42 later, I've got this Pittsburgh Pro from Harbor Freight. You can see it's got 7 different styles, and that was the cheapest one in the store. And indeed, it features the safety bits. Nice, sturdy. It doesn't wibble wobble. That one fits. T15. Trust me, this will be better for everyone. And I'm not keen about getting carpal tunnel surgery. Works like a charm. These guys are being paid by the number of screws they can install. There's one more here. Okay, I think the rubber piece has to come off, and there are additional fasteners underneath right there. You can see that there are additional fasteners here. I'm not gonna bore you with that half an hour of close fight I just accomplished removing this piece of condom, but it's off. It's some kind of rubberized, plasticized, hard freaking material. I don't see any marking on it, but as you can see, this is a hole here that I had to tear so that it would come off, and this is the pivot. This is the pivot arm basically that holds this piece that protrudes to the front, that foot. I think it's called a foot. And you can see that this piece, this plastic piece, does not come out unless you take it apart. It's in there good. So there's no access from the front. You know, if you get in here and you try to wiggle something, you know, it's just not coming off. I really don't know what this thing does. Anyway, I don't think it's for users. You can see this is the lever that pops open the locking mechanism, and that locks the blade in. So that's how that works. Anyways, we got a couple more screws here to come out, and probably these dampers, and then we can finally get in. But for that we need a couple additional tools like this. I think it's a Phillips one. Bumper comes off. The other bumper comes off. I don't know what these do. I'm guessing they cannot fill out the space with this rubberized piece. And when you make something like this, it has to have a constant wall thickness, so you cannot add like thick sections to it. As you can see, they can add these ribs. I don't know how much you can see it on the footage. So they can add these ribs, but they are thin. But otherwise, everything has like a constant thickness. Otherwise, the material, the plastic, would not fill the mold out properly. Looks like these are longer than the clamshell bolts. So you can see they are about 1/4 inch longer. These are from the clamshell, and these are from the mechanical part, the business end. Oh, huh. Not much. I'm telling you, there isn't much. Motor. This is probably the motor controller. This is the toggle switch. I think this is just a connection to the battery. That's where the battery connects, some electronics. And then there's the FBI tracker. You can find these on every tool. There's a barcode on it, that's it. There's not even a part number or anything else. This is not for the users, this is not for the stores. They put these in the factory. Interesting here, so this is the rear end bearing, this is the drive end, and you can see in the clamshell there's a plastic insert here that's supposed to dampen some of the vibration that is coming from the motor. So let's see if this guy, it will not separate. There you go. Here's the other clamshell. There's some plastic residual in a clamshell. It says PA6, so it's a polyamide, and GF30 TPE. So polyamide 6, which is essentially nylon, and then glass fill 30. Some people say they put the glass fill in to make it stronger. Some people say that they put it just to make the plastic cheaper, because the plastic is real expensive. And then the TPE here, you can see that says TPE. That is this overmold. It's some kind of butyl rubber, or some kind of rubber overmold. These will disintegrate if you put, you know, some solvent on it, especially acetone. This is just gonna turn into mush, which happened to me on some of the tools. So you gotta be real careful when you are, you know, painting. The paints have solvents in them, that you don't touch these with your hands, you know, that has those solvents. I gotta tell you, buddy, this smells so bad. So you can see the burn up right there. So the stator coil on the motor is burned up. I can see that phase is completely burned, and it looks like one of the bus bars here. You see that bus bar right there? You see the bus bar? So this bus bar is missing the insulation. It's bare copper. So the insulation came off. You see it popped off from here, and because of that, I think it might be touching the fan. You can see that the piece of wire clearly came off. It's like it wasn't properly set, or the varnishing process didn't lock it in place. So we're gonna go and take this apart. This actually just should slide out. So what we have here is the stator, and then we have the motor rotor. There you go. That was easy. So that gear just popped out from the drive mechanism here. As you can see, on the drive side, they also have an O-ring that is inside this aluminum housing. And so that O-ring also supposed to dampen some of the vibration that is coming from the motor. And look at this. This is just a wire that goes inside the casing here. So this is all aluminum. This is die-cast aluminum, 2 clamshells that sandwich the drive mechanism, and it just plugs in here. There you go. So what it does, it operates this light in the front. So when you depress the trigger, the electronics will turn this light on so that it will illuminate the area where you are doing the cutting. I still don't get how this part comes out from here. There are just certain things that I obsess more about than other things. You know, one would think that this has to be serviceable, like the new iPhones in Europe. You know, they have to be serviceable, and so Apple has to provide servicing kits and instructions to the users if they request so. That's the new European law, I guess, or regulation. And you would think that, you know, this instrument might cost, you know, $150, and if there's a 5-cent part that breaks on it, the user's supposed to be able to fix it, you know, some simple stuff, but this is definitely not done to be serviceable, this lever. So I don't think they expect you to remove the boot from the mechanism. So let's go and see what's up with the motor. This rotor is supposed to come out. And you know what, I'm gonna put the gloves on because everything is so sharp. I don't want to get a cut. Brand new gloves just for this occasion. So this is supposed to press out. There you go. So we got the rotor, and the rotor has permanent magnets on it. So you can see the permanent magnets. You can see these are pretty strong magnets. And this is a 4-pole machine. So there are the magnets. So there's 1, 2, 3, 4. You know, it's thin lamination. So it's steel that is cut out from a sheet to this shape, and then it's stacked together, and then there's a weld typically here. So there's a weld that holds the lamination together so that it doesn't fall apart. You can see the welds in this area here. And they also sometimes have interlocking features in the rotor. And those interlocking features, when you press the stack together, then it's going to make a solid stack. Obviously, when this is being put together, the assembly worker is not going to sit there and count out, you know, that, hey, I need 40 pieces, not 39, not 41. But it's all an automated process. And because of that, the manufacturing is set up that way. So it's got a this is a 625Z bearing, and you can see that it's got 2 metal shields. So it's shielded on this side and it's shielded on that side, which is perfect for this job because we don't deal with brush powder anymore. You know, for the traditional motors that are not brushless, this is a brushless motor. For the traditional motors, you ended up with a lot of brush dust, and that can get into the bearings and ruin it. So on the drive side, we have a big bearing here that is has a rubber gasket, a rubber seal on both sides. I cannot read the part number because there is this washer, and the washer is not allowing me to read the numbers. Also, I wanted to point out here that these magnets are glued in, so there's typically some kind of adhesive that is administered in these cavities here, and it fills out the entire cavity and it locks in the magnets. And you can see that on the edges here, this is a some kind of powder metal balance ring, and as you can see, it's got a brass tone, so it's probably made out of brass, and there is the balancing hole on it. So these rotors are balanced in 2 planes, you know, typically in this plane and this plane. It's really hard to point with something that is magnetic around a rotor. There you have it. So these balance rings are brass, and these are the balancing holes. Because you can see this is a fairly small diameter, and it probably has a high speed. I need to put it somewhere where it's not going to pick up all the metal parts. So here's the culprit. As you can see, the stator is completely burnt up. So the stator has 6 poles, the motor has 4 poles. And here in the stator, you can see this is the stator. These are the stator coils, and this one is completely burnt up, and that one is completely burnt up. So these 2 are connected in series. So this would be 1 pole pair. And then on the non-drive side, we have a PCB and this PCB is bolted on here. These are the bolts that hold it in place, and we also have a soldered connection, and that soldered connection basically connects the field coil to the PCB. And then on the PCB we have Hall elements, so you can see the little black spots here on the bottom. So those are the Hall elements, and that is basically telling the computer where the rotor is in a spatial position relative to the stator. So the part number on the stator is 27403-88002, and it says 19F21B. I don't think they sell this as a separate entity so that I would be able to purchase it, because you can see that this whole thing is soldered together. So this is the controller, basically the inverter. What it does, it creates a sine wave, and then it looks after the rotor, and depending on how much you depress the trigger switch, it is gonna generate sine wave with some kind of amplitude. This is a 24-volt motor, so I'm guessing that the voltage that is coming out from here is somewhere in that range. And so you can see the 3 phase cables here. So we got the yellow, the white, and the blue. Those are the phase cables that are feeding the voltage and the current to the motor. And then this is basically the blue and the black are the DC input. As you can see, the blue is attached to the battery, and then this red basically goes to the switch, and then we have a huge diode here. This is called a snubber diode between the 2 terminals of the switch. Also, you can see that the switch has a lot of tiny wires coming out of it, and what they do, that is the potentiometer that is feeding information to the brain box here. So this is the actual controller. So it's feeding information to the brain box, and it is basically telling the brain box how far you depressed this switch, and so it will make the motor go faster or slower. We also have a breakout board here with 2 capacitors. So these are just external capacitors for the inverter. When you're doing the switching, when the inverter turns it on and off, on and off, on and off, every time you do it, it is gonna create a voltage spike, and then these capacitors help to smooth that out. So this is this is pretty much it. I don't think this is going back together. So what I'm doing here is I'm tapping into the phase leads. It doesn't matter which one, because on both we should see a sine wave. There's the battery connected, and when I'm triggering it, you can see a slight. It's an auto, so a slight shadow pops up, but then it disappears immediately. So what is happening when the controller energizes the field coil? It is expecting a certain kind of signal coming back from the Hall effect sensors, because then the rotor, is spinning and it's affecting the Hall effect sensors. If it doesn't get any feedback from them, obviously the rotor is not spinning yet, it's energized, so it will cut the power. I think that's what it's doing. Again, here's it again. So you can see a little blip, and then it's gone. Now take it apart before it blows up on me, because this is 4 amp hours, 24 volt, so this packs a lot of energy. Now, I don't want to waste that energy in the wrong way. I looked up these part numbers. So as you can see, there's a part number here, 4823F12, and then there's one 1704D0404. That didn't yield anything on a Google search. I also looked up these part numbers here. Nothing came up. At this point, you know, it would be feasible if you have the time and a commitment to rewind this. So essentially clean a certain area on the coil and then figure out what the copper size is, order new copper, and then you know, remove the windings mechanically, unsolder this in, remove the windings, and then rewind it. Now the problem becomes that all these insulators are, you can see, you know, both insulators on both sides are melted, completely melted. And so the lamination, when it's made, it has a sharp corner here where the winding is wound on it. And when you are winding and you know there's no insulation, then you can nick the wire, and that can cause a short on a phase. I think that's what happened here. This one had a phase short, and essentially, you know, the resistance of one of the coils is not the same as the other one, so you have a low resistance in one of the coils, and that is enough to create more heat because it's a lower resistance, you know, with the same voltage, and basically that can heat it up in no time and cause this kind of failure. You know what I'm thinking? I'm gonna take this apart, unsolder it. I cannot screw it up anymore. So let's just leave a little bit of wire here. I don't know. I'm gonna do it in a nice way. These 3 bolts hold the Hall effect PCB. I'm gonna attempt to desolder these. So as you can see, it came off. So again, this is the PCB that holds the Hall effect sensors, and you can see the Hall effect sensors here. So there's one there, one here, and one here. They typically come three of them, you know, 120 degrees apart, and then you can see the marking here for the phases. The motors are typically being called as U, V, and then W. So the yellow is the W, the white is the U, and then this is the blue is the V. And you can also see the black chart marks from the wire here burning up. And so we got 3 phases. Okay, so you know, this is one phase pair, this is one phase pair, and this is one phase pair. And then here you can see the wires are twisted together. So that would tell me that this is connected in delta. You can have a Y connection, you can have a delta connection. The voltages and the currents essentially change within the motor. So let's look at the resistance. So here's the resistance for one of the phases. So 0.1 ohm. Here's the other phase. And you can see that's toggling between 0.1 and 0. And then here's the third one. That's also 0.1 ohm. So obviously this one that measures a smaller resistance, that is the one that kind of burnt up. I'm pretty sure that it has a phase short. It would be nice if they sell these. I would be able to swap it out in no time and put it together. I'm pretty sure that this motor is being used for other types of Kobalt power tools. Again, the part number on it is 2740388002. But as it stands right now, that's pretty much a dead end for this Sawzall. What I'm gonna do is just box the parts and put them in a corner somewhere in the shrine for good safekeeping. Maybe one day I'm gonna use the parts for something. So the part number on it is KRS 1824B-3. It says it goes 3100 SPM. I'm guessing that is strokes per minute. So the business end, that is the business end, can do 3100 strokes, and obviously there's a gear reduction here, so the motor spins a lot faster than that. If you need any of these parts, drop me a line in the comments and I'll be happy to cut a deal for you. And if you guys like the video, please give me thumbs up or just like it. And if you want to see more of these videos to come, leave a comment or just subscribe to the channel. See you on the next one. Bye.